Hello, Mr. Gehman's Future Physics class. My name is Octavio Miranda, and today I will be working number 63 out of chapter 11 in my textbook. The problem pertains to angular momentum and the conservation of it. So right now all I'm doing is setting up an example Mr. Gehman's probably shown y'all before, and it is about how an object in linear motion can have angular momentum. The only thing I probably did differently than him is I labeled the distance from point P to my object of mass m, a length of L, and I made P to my velocity vector r. And so this is what we're going to be using to solve for number 63 in the textbook. And you see that you can set up the angular momentum equation so that it is mvl sine theta instead of L mv sine theta. And using your trig identities, you'll see that for any combination of L and theta, you will get that resulting side r when you solve for it. And you are just left with the equation angular momentum equals mvr. And just a side note, this equation only works if in this case a ball, but if this object is coming at an angle perpendicular to that point P. So this is exactly where a student might get confused on this problem, is that there's a ball-child merry-go-round system, and the ball is being thrown at a child at an angle that is not perpendicular to the center of the merry-go-round. So what you're going to do is you're just going to componentize the velocity vector. And here I'm drawing the diagram just to help you visualize the problem. I'm drawing the diagram that I did last slide. And here is the x component of velocity, or horizontal component, whatever. And the y component of velocity is actually not going to be important in this because sine of 180 equals 0, and so math. Yeah, it won't have any effect on the angular momentum of the merry-go-round. So now that you have your x component of velocity equals v cosine of phi, the angle given to you. And now that you have that, you have pretty much everything you need to solve the problem. So you use angular momentum conservation, and you set the initial angular momentum equal to the final angular momentum. And for your initial, you plug in that rmv, but your velocity is going to be just the x component of your initial velocity vector. So it will be v cosine of phi. And you'll set that equal to the final angular momentum, which is I, moment of inertia final, times angular velocity. And what we're going to be doing in this problem is we're going to be solving for angular velocity, but the fact that it is in variable form allows you to be able to apply it to solve for any part of the problem. And so hopefully this will help you solve for more difficult problems in the future. So right now all I'm doing is I'm taking the moment of inertia and I'm solving for it, because you get the moment of inertia of the merry-go-round in the problem, but you have to solve for the moment of inertia of the child and the ball. And it's pretty easy because they are just treated as a point mass at the edge of the merry-go-round once the boy catches the ball. And so you will just get the mass of the child times the radius of the merry-go-round squared, plus the mass of the ball times the radius of the merry-go-round squared. And so you can now, which is what I do whenever I plug in the numbers, you can combine the mass of the ball and the mass of the child and multiply that times the radius of the merry-go-round squared, just to make things a little simpler. And so now I'll be plugging in all the numbers, and there they are. The radius of the merry-go-round, the mass of the ball, the speed at which the ball was coming in, and the angle, cosine of the angle. And I divide that by the moment of inertia of the objects, and that is how you get your final answer. I hope this was helpful, and I hope it will help you with any other angular momentum problems you have in the future. Thank you.